Hello. In the previous video, we had tried the problems on electrostatics up to the question 30, and we'll be starting off from the 31st bit in this video today. And what it says is that you have to find the place or the distance uh, along the perpendicular bisector of a line AB, which is carrying charge at the point charge Q at the points A and B, separated by a distance d. So that line AB is of length d, and we have to find the maximum force that is experienced on any given position on any charge Q which is placed along that perpendicular bisector. So we need to obtain the position where that third charge small q needs to be placed so that it will experience maximum amount of force. Now, as far as the question goes, what we find is that if we have two charges supposedly separated by a distance d, which are on the points A and B, and this distance is obviously d, I'll write it here. So now you need to find the distance along that perpendicular bisector where a third charge q, if placed, experiences a maximum force. Now this is as per the condition of maxima and minima. So what we do over here is that we consider, let us assume that this is placed at a distance x, and so these distances are obviously d over 2 on either side. So what that results in that this is perpendicular, so the lines from A through, let this point be P, so AP will be equal to AB, which will be not AB but PB, and that is equal to d over 2 squared plus x squared under root. That is the distance. Now the force that the charge q will be experiencing will be something like this. It will be experiencing a force from the positive charge q along AP, and also a force along that line from the charge at the point B. And so both of these forces will be obviously equal in magnitude because they have equal distances from the given charge. So that means the magnitude of the force, let that be F. And as we know that if two forces are equal in magnitude, the resultant of them is going to bisect the angle between them. So if this is the point P, and these are the two forces that are acting along this line, so this is force F and F in magnitude, of course, because the directions will be different, of course. So in that case, this will be F prime and this will be F when taken in vectors, and the resultant force is going to be bisecting the angle between them, and let this angle be some angle theta, which is obviously this angle theta over here, right? So let me draw that triangle again over here. So this is that, not exactly the triangle, but I have considered the triangle as a whole. So this is the point P, which is lying at a distance x, and this is d over 2 on each side or on either side, and so this angle is going to be theta, and from that we can obtain the cosine component. So both those cosine components are going to act along that direction. So F net is going to be equal to F cosine theta plus F primed cosine theta, and obviously because the magnitudes are the same, that is F is equal to F prime. F is equal to F primed when considered in terms of the magnitude. So we have this, let us say 2F cosine theta, and that's going to be the resultant. So let's find the resultant first. So we have 2, and about the force, well, the force is equal to KQQ over the square of this term, that is either AP or PB, and that's going to be d over 2 squared plus x squared, as it is because we are considering the square of this term, so the root over is taken out. And then with this value of force that is acting, we need to find cosine theta from this triangle. Now what is the value of cosine theta? Well, cosine theta is actually the base, that is x. Cosine theta is equal to x over this hypotenuse, which is exactly equal to this value that we have obtained, that is d over 2 squared plus x squared all under root. When that is taken over here, so this is x over d over 2 squared plus x squared under root. So what we find is this is 2kqq times of x, that x can stay over there, and then that entire thing divided by d over 2 squared plus x squared 3 over 2. So that is the value of the force that is acting. Now when will that force be maximum? We need to find the position where the force is going to maximum. So we are going to take the derivative of the net force with respect to the position, and we are going to set that to 0, and that is the way to find the maximum or the minimum of any given value with respect to whatever parameter we are seeking. So in that case, this will be equal to, so we just equate this thing, or we take that as a 2k, q and q, they are all going to be constant terms, because we are taking the derivative with respect to x. So this is d over dx of this term, that is x over this term, well, that is d over 2 squared plus x squared raised to the power 3 over 2. Now taking the derivative over there, what we get, and we obviously set it to 0. Now taking the derivative over there, this entire thing can go to the other side and we can just get rid of that. With the derivative of this term, that will be equal to, this is in u by v form, so this is d over 2 squared plus x squared raised to the power 3 by 2 and d over dx of x. This is the first thing. V du minus u dv, so x lies out, and we have d over dx of this entire bracketed term, that is equal to d over 2 squared plus x squared raised to the power 3 by 2, and all of that divided by d over 2 squared plus x squared raised to the power 3 by 2 squared, which is again 3, and this is equal to 0. Because this is equal to 0, we can just set this, we can take this to the other side and that goes out. So all we are left with is the numerator term. So what we have over here is equal to d over 2 squared plus x squared raised to the power 3 by 2. That remains as such. D over dx, dx over dx is going to be equal to 1, and minus x, well, as for the second term d over 2 squared, that is a constant value, so that goes to 0 when taken derivative. We are concerned with the entire thing as a whole, so we first have 3 over 2 times of that entire parameter. Using the chain rule, we have obtained this, so x squared, and this is raised to the power half, and then we go inside that term, inside the bracketed term, and we lose that constant term, that is d over 2 squared, and the derivative of x squared is obviously going to be 2x. So now this is equal to 0, and with that one being equal to 0, what we get is we have d over 2 squared plus x squared raised to the power 3 by 2 to be equal to, this x multiplies with the other one, so and the 2's get cancelled out over here, so we have 3x squared on the other side, d over 2 squared plus x squared under root, or raised to the power 3, raised to the power half. Now half, and there's 3 over 2 there, so this actually cancels out with this entire term to give the power as 1, and we have d over 2 squared plus x squared is equal to 3x squared. So that means we can take the x squared to the other side, so we have 2x squared, so x squared is equal to half of d over 2 squared. So that gives us x to be equal to d over 2 root 2, and that is the value or the position along that perpendicular axis where we are going to achieve the maximum force on that small charge q, or that charge small q, due to the two q's that are there or at the points A and B. Now also in that question it has asked to obtain the magnitude of the maximum force. So if you have the value of x with respect to d, so you can use that formula and obtain the value of the maximum force. Then we move over to the 32nd bit where we wish to obtain the, again there's a condition probably of maximum force, so let me read that out. Now there are two particles A and B each carrying charge q and are fixed at a separation d, same as above. A particle C having mass m and charge small q is kept at the middle point of the line AB. So now this is in the middle, and now it is displaced through a distance x along the perpendicular or to that point AB, or to that line AB. What would be the electric force that will be experienced by it? Well, we have a brief idea about that, as considering the question that we have done previously. Now second bit, it has asked that we assume that x is much less than d. We need to show that the force is proportional to x. Okay, and the third bit is that under what condition will the particle C execute simple harmonic motion if it is released after such a small displacement, and we need to find the time period of oscillation if the conditions are satisfied. So in this bit we have exactly the same thing as the previous one. The only thing is that the displacement is now very less, but first of all the conditions are almost the same, exactly the same. So we have the two charges again, and we have the perpendicular bisector along which we are displacing the charge small q with a mass. Now mass has been assigned to it as m, and it is displaced, let us say, through a distance x. Now the magnitude of the force obviously we have obtained. So the first bit of the question is to find the magnitude or the expression for the magnitude of the force, and we know that because we have just obtained that, that is 2kqq over, and there's an x obviously, and that divided by d over 2 squared plus x squared raised to the power 3 over 2. This is what we have obtained, and the maximum obviously we know that when x is equal to d over 2 root 2, that is when we are going to obtain the maximum force. What it has said in the second bit of the question is that, if you remember, that you can go back and see yourself, that if this distance that we have, that is x, if that is much less than that distance d, for x much less than d, we'll have to show that this force is directly proportional to the displacement through that perpendicular bisector, that is x. Now the charge was initially over here actually, and that has been taken to that position. So that has been displaced through a distance x along that perpendicular bisector. So what we need to show is that the force is proportional to x in that case, if x is much less than d. Obviously x squared is going to be much less than d squared, or d over 2, doesn't really matter. So now f in that case can be rewritten as like this, that is, we keep the x over there, but in the denominator what we can do is we can take the d over 2 out of it, and d over 2 out of it means we have the cube term now, with the power term acting on it, and then obviously over here what we get is 1 plus 2 over d and x, and that is squared. Now x is much less than d, and x is going to be even much less than d square, x square. So this term entirely is roughly going to be equal to 1, because that second term in that bracket is going to be very, very less than 1. This term is going to be very, very less than 1. So that is why less than, not greater than, less than 1. So that is why you have that kind of a condition that we can neglect that term with respect to 1, and we just have 1 over there. And d is, as you know, is fixed in this case. So what we obtain is that the magnitude is going to be, well, you can take the cube of 2 and take it up, so we have 16k q over d cubed, and all of that is constant, as you know, because they are fixed values. Only thing we can change, that is in our hand, is x. So obviously force is going to be proportional directly to the displacement along that perpendicular bisector. Now with this condition available to us, we need to see if there is going to be any simple harmonic motion, or we need to seek the condition under which this will be a simple harmonic motion. Now the forces that were acting from these two charges on that small charge q, that would have been repulsive had that positive, had that charge q been positive. Now if we have q to be negative charge, then the forces would be attractive. In the previous problem we had the q charge to be positive, and that's why the force was acting in the upward direction. But if this q charge that is negative in nature, then we'll have the two charges q which will be applying forces towards themselves. They will be attracting it, and hence when we displace it along this direction, this is our displacement, it will be attracted towards this line, and then with the force acting due to the attractive force, it will be moving further towards this direction, and then it will be further attracted by the two charges along that line. So in that case it will be executing a simple harmonic motion. So the condition that we have that this particle executes a simple harmonic motion is that the particle has to have a charge that is opposite to the charge carried by these charges. So if these charges are positive, that small q will have to be negative in order to execute SHM, and if these two charges are negative, then the small charge will obviously have to be positive. But under the conditions that we have been provided, the charges capital Q are positive, so the charge small q needs to be negative. Now if there is a simple harmonic motion, we need to obtain the acceleration, or the time period of that simple harmonic motion. Now what we know from our previous studies on simple harmonic motion is that the time period is going to be equal to 2 pi, and under that root what we are going to have is displacement over the acceleration. Now in that case the displacement we know over here is through a distance x, because we are displacing it through a distance x. What about the acceleration? Now we need to obtain the acceleration. We have the force already when the displacement is small. Now force over the mass is going to give us the acceleration. We have the mass of the particle to be m, that force upon mass is going to be acceleration. So we are going to keep that force over here, 16k q multiplied to x over d cube. We extend that square root term, and then we have the mass that should have been divided over there, but that goes up. Now this x terms, they cancel out, so what we get from this is d cube can go up as well. So we have 2 pi m d cube 16k q. Now in case you wish to obtain it in a whole form, then you need to open up that k, which is 4 pi epsilon naught times 1 over 4 pi epsilon naught. So in that case you are going to get a few terms can get cancelled out in that case, and then you have the value. So you can use that formula of k, that is 1 over 4 pi epsilon naught for air or vacuum being the medium, and then you can obtain another form of the expression if you wish to obtain that. Now in the 33rd bit, what it asks is that we need to refer to the previous problem, the same conditions, but only thing is that The particle C that was in the middle, that will be now displaced not along the perpendicular bisector, but along the line of the AB, along the line AB, and obviously the displacement will be small, and we'll have to obtain the conditions under which it will be executing a simple harmonic motion. And also the case that we need to obtain is the time period for any small displacement. Now the only thing that is going to be different, if at all, is in the expression of the force that we will be obtaining for the that which is acting on the charge q, which is at the middle. So let's see what we obtain. So in this case, we have the same arrangement where we have A and B to be separated through a distance d, and the only thing is that the charge that is present at the center, that will be now displaced through a distance x along the line AB. It can be either way. I have pushed it towards B. Now what happens is that now it experiences a certain force from both the charges. It's already it was actually experiencing zero force when it was at the center because of the cancellation of the electric field as well as the force at the center, because of the equal forces from either side, quite clear from the dimensions. But now we have a displacement towards, let's say, towards B. So the force that it will be experiencing from A will be along the line, let this point be P, well, along the line AP, because it will be repulsive in nature. We are assuming that all the charges are positive. So in that case, it will be experiencing KQ over d plus x, because the distance is now x, so d plus x whole squared, and it's along AP. And what about the force from the charge at B? Well, it will be KQ over d minus x whole squared, and it will be experiencing that will be repulsive as well, and that will be along BP. So from B towards P, repulsive in nature. Obviously, the magnitude of the force due to B, it will be greater than the magnitude that due to A, because the distance is slightly smaller in case of B, so it will have a greater impact. And as a result of that, the net force that we can obtain will be equal to FB minus FA directly, and that will be equal to KQQ, and we can take the LCM, and that will be d squared minus x squared whole squared, and at the top we will have quite clearly, we can see that this will be somewhat of the value minus 4 times of dx. That's d minus x, d plus x whole squared minus d minus x whole squared, so that is actually plus 4 dx. Now with that value available to us, what we wish to determine is that now we have obtained the force that it will be experiencing. As far as the question is concerned, we can go back to that. So firstly, we were to determine the force, and which we have obviously determined. Then for x much less than d, what would be the expression for the force? We'll have to show that it directly depends on x, and from that we'll be obtaining the condition for the particle at point C to be executing SHM, and then we'll be obtaining the time period of the simple harmonic motion. So this is the required expression for the force. So this is the first bit, and this point is actually P, is C, not P. So now what we need to take is that if x is much less than d, then what we get over here is that we can have the net force in magnitude now to be equal to KQQ, and we keep the 4d and all of that x outside. And what about the denominator? Now in the denominator term, if we have d square as common, then we can take d raised to the power 4, and within the bracket now lies 1 minus x squared over d squared whole squared. Now x being less than d, x squared will be even smaller than d squared, and when compared to this this value, that is 1 minus of that, is nearly going to be equal to 1. So this is nearly equal to 1, and so with all those terms out there being constant, d is going to cancel out with one of d in the denominator. We will have the force, the net force that acts on that particle carrying charge q will be proportional to the displacement. The greater the displacement, the greater will be the force. Now the condition for SHM in this case, well, in the previous case, if you remember, we had obtained that the charge has to be negative when it is placed along the perpendicular bisector, but because it has to be attracted with the same force, because if it is repelled along that line, it will go away and it won't return. So there is no question of SHM in that case. In this case, however, it doesn't really matter. It just has to be the same nature as that of it doesn't really matter whether it's of the same nature or not, because if it is attracted by one of the charges being negative, then it will be attracted by the other one as well, and if it is repelled by one of the charges, it will be repelled by the other one at the other end as well. So in both the sides, it's going to experience some force or the other. Attractive or repulsive, it doesn't really depend on the nature in this case, so it's going to execute SHM anyway in case of a short displacement along the line. So it doesn't really matter. The condition here is quite clear. If the charge can stay as it is, it just requires that small displacement x along that line. Now again, if we are to obtain the obtain the time period of that SHM, we need to use the expression. So this is part B. Part C, conditions are not really required. We know the conditions, they are quite clear. So all we need to obtain is the time period, and we know time period is equal to 2 pi root over of displacement over acceleration. Now we clearly have the expression for force over here, and from that we can obtain the acceleration. Now the acceleration will just be force divided by mass. So this expression can have d cube over here, so we can write that properly. Now this displacement over here is x over the acceleration being equal to all of that value that we have over there in this box, in this circle, including the x obviously. So we have k, q, 4 can be taken over here, and then we have d cube can go up, and the x lies there multiplied to that term. So the x's get cancelled out, so we have 2 pi root over of, we have the term, the 4 can come out and cancel out with the 2, so we just have a pi, and d cube over, well, this is k q. You can use, oh, I forgot about the mass. The mass was to be divided by the force, so the mass term when divided by this force gives the acceleration. This was the force, the mass when divided goes up, so there will be a mass over there as well. I hope you don't mind that interruption with the mass. The mass has to be there because it has to be the acceleration. So I'd forgotten to keep that mass. Now I've kept it over there. So this is more or less the expression. You can obtain various forms of that expression by again expanding that value of k, that is 1 over 4 pi epsilon naught, and then you can use it to obtain a better expression, a good looking expression, rather than the one I have given you. But more or less this is the time period that we have obtained. So that solves the 33rd bit. Now moving over to the 34th, it seems pretty easier and straightforward as well. As you can see, we just need to obtain the electric force that is experienced by a charge, which is we just need to obtain the electric field that is at the position of the charge. The value of the charge has been provided and the force experienced by it has been provided. So the magnitude is obviously F is equal to QE. So from that we can obtain E to be equal to F over Q. So it's absolutely nothing. So no need to do that. You can try it yourself and predict the answer. Then again in the 35th bit we have two charges, so positive and negative, and they are fixed at a separation. We need to locate the point where the electric field is 0 and the electric potential is 0. Now electric field is obviously 0 at some position which is on the side of the 2 microcoulomb charge, because that is less in magnitude, and I've already explained the case where we can determine the position. You can look for that in the previous videos, similar kind of videos. The only thing we can look up to is the electric field. Now the electric potential to be 0. Now the electric potential to be 0, it will be exactly in between those charges, because potential being a scalar quantity, you just need to obtain that in between those charges. So there won't be any problem with that. Had there been 2 positive or 2 negative, there wouldn't have been a point where the potential would have been 0. Everywhere you will be adding up the potential, so that's not a big deal as well. So it will be somewhere in between those two charges. You can obtain that easily. In the 36th bit we have a point charge which produces an electric field at 40 centimeters distance. What is the magnitude of the charge? Again, an absolute nothing, easily can be determined. So such problems are not a big deal, not to be taken too seriously if you know the basics. What I'll be concerned about is the 39th one, which seems pretty big, but as I will be doing it, you'll find that it's pretty simple to try that out. We have a positive charge q to be distributed uniformly over the circular ring of radius r. A particle having a mass m and negative charge q is placed on its axis at a distance x from the center, and we assume that the distance x is much less when compared to the radius. We need to find the force on that particle with that assumption of dimension that has been provided, and also the time period of oscillation of the particle if it is released from that point. Okay, so it's an interesting one. Let's try that. So that's more or less the arrangement. It's not 34th, it's 39th one, where we have a charge q to be distributed uniformly over that ring of radius r, and obviously it will have charge distributed over its length, means that we'll have a charge per unit length, that is per unit length it will have a charge q over 2 pi r, and if we are taking a length dl from it, then that will carry a small charge q over 2 pi r times of dl, that will be equal to dq. And we'll consider two such diametrically opposite points where we'll be taking the dq segments, dq in dl of course. So why? Because we will be seeing why actually. So two such segments have been considered, very very small ones. We will be taking the electric field at the point considered, which is lying at the distance x. Now if we are considering a positive charge at that point which is lying at a distance x from the center of the arrangement, this is the center of the arrangement, so from the center it will be pushing it towards this direction, that is dE, along that line, and also from this bottommost point, the one that we have considered the element, it will be pushing that one as well with a magnitude, let's say dE of the same magnitude, but dE prime because the direction is different. So now we have, supposedly they are at equal angles theta. They have to be equal angles because they are, if you look at the dimensions, this is a circle, and from that circle we are getting those directions. So diametrically opposite points, obviously. And this distance is r, that is the radius that has been shown, and the horizontal distance, as you know, is x. So this distance will be r square plus x squared under root. Now with that distance, both the distance, actually the upper and the lower distance, both of them will be the same, considering the dimensions again. Now if we are to take the components of those vectors, so we have dE prime cosine theta along this direction, and also dE cosine theta along that direction as well. So that will result, the addition of those two will actually result in the total field that is acting along that direction, that is dE net. And the other component, that will be dE sine theta, that will be acting along this direction, and the dE sine theta, dE prime sine theta, and dE sine theta will be acting in the downward direction, both those being equal and opposite, because dE will be equal to dE prime when we consider the magnitude. So both those forces being equal and opposite, the sine components, they will cancel out each other. So that is the reason behind taking these diametrically opposite points, because all those diametrically opposite points, their sine components will be cancelling out each other, while the cosine components will be acting along that axis every time throughout that entire cyclic, throughout that entire circle that we are going to integrate. So as a result of that, we'll be having dE net to be equal to, we can say, because these two are equal in magnitude, so that will be equal to 2 dE cosine theta, because dE prime is equal to dE. And what is the value of that dE? dE will be equal to, as you know, is equal to k dq over the distance squared. Distance, as you know, is this one. When that is squared, that is r squared plus x squared, simply as it looks like. Now, as you know, dq has been provided, and that is going to be equal to, so dE being that, we have dE net to be equal to 2 times of dE, that is k, over r square plus x square. We are going to keep that, and dq, we are going to put the value, that is q dl over 2 pi r. And then for the cosine theta, we will be considering this triangle over here. So this is theta. As you can see, cosine theta is simply the base over the hypotenuse, which is equal to x over r squared plus x squared. Hypotenuse means this has to be taken under root. So all of that being put together, we have dE net to be equal to, I will write it over here, that is equal to, the 2's can get cancelled out, we'll take care of that, and then we have q, kq over pi r, and then we have x, we have dl, and we have r squared plus x squared raised to the power 3 over 2. That is what we have over here, and we are going to integrate it. The integration is obviously going to be along will be the semicircle or semi-circumference, because the total circumference will be covered when we take one of those dl elements and take it halfway down, and the dl element at the other end, diametrically opposite end, and we take it up halfway. So in both of those cases, so this dl is integrated along this direction, and that bottom dl is integrated along that direction. So as a result of that, we cover the entire circle. So dl has to be integrated simply from 0 to pi r being the circumference, the half of the circumference, the total circumference. So in that case, what we have is, because the 2 factor was over here, which got cancelled out, so it would have been 2 pi r either way, but just to show the cancellation of the sine components, we took this procedure. So now we have the E net to be equal to the integration of dE net, and integration, as you know, will be over dl, which will be from 0 to pi r, and that is going to give us pi r. So dl, when integrated, is going to give us pi r simply, and that pi r is going to cancel out with this one, so I'm not wasting any time with that integration. So we are left with the expression k q over r square plus x square raised to the power 3 over 2, and there will be an x over here as well. Now the second part of the question, so this is actually the force that is going to experience, the field that it's going to experience. Now the force for a charge q placed at that point, so let me change the ink for you for showing you the charge over there. So the force on the charge q, which will probably be placed over here, that will experience a force of q times of E net, so that will include a q over there, right? q times of E net, that will include a q over there, and this will be actually the force experienced by that negative charge q. Now this is negative charge, so it is going to be attracted towards this direction. We'll see what the attraction does, but first up we have to consider the distance, the distance x being much less than that of the radius. So we take another page and we discuss that. So now we take up that expression for force, that is the net force that is acting, that will be equal to, and that is attractive obviously, so that will be, if we put the vector over there, it will be actually negative to x vector if we are treating the x direction as the x vector, and not the unit vector, but this is actually having a magnitude of x, and it is exactly opposite because it will be attractive. So k q q over, what was the rest of the expression? Well, the rest of the expression was the x was certainly there, and at the denominator we simply had r squared plus x squared raised to the power 3 over 2. This was the expression. Now if we have x to be much less than r, x squared is going to be even lesser than r squared, and as a result of that, what will happen to this is that we put this condition over here, and what we get is simply minus k q q, the x vector remains as such, and this thing over here, r taken out of that bracket, with the 3 over 2, we have r cubed left, and in the denominator we have x squared over r squared raised to the power 3 over 2. Now when compared to this 1, this nearly goes to 1 only, because 1 is much greater than x squared over r squared, so it doesn't really matter whether you add that or not. So this is going to be the expression for the force that will be acting on it, the attractive force, and as you can see, it is directly proportional to x over here as well. Now if we are to determine the time period of that oscillation, then the time period of that oscillation will be equal to 2 pi root over of displacement over acceleration, and the acceleration is obviously going to be the force over the mass. So let's see whether the mass was given. Actually there has to be a mass, because you cannot obtain the acceleration in any other way. So this force over that mass, the net force over that mass, is going to give us the acceleration, which is equal to, we'll just be concerned about the magnitude of that, so that's going to be k q q over r cube. M is going to get multiplied to that factor in the denominator. So what we have is that 2 pi over under root, we have displacement x, then we have k q q over mr cube times of x. The x's are going to cancel out, so we have 2 pi, and mr cube goes up, and k q q remains in the denominator. Again, you can have a better form of this expression by expanding that, or using that value of k that we have, electrostatic force constant, that is 1 over 4 pi epsilon naught, and you put it over there and you plug in that value and you obtain the expression there. So that's the 39th bit done and dusted. Now we have the 40th one, where we have a rod of length L carrying a total charge Q to be distributed along its length, and it is bent in the shape of a semicircle. We need to find the magnitude of the electric field at the center of curvature of that semicircle. So let's try that. And to save time, I have done it already. As you can see over there, we have a semicircle, and we'll use a certain radius now, although we know that the semicircle is of length L, and it carries a charge Q that has been provided uniformly distributed over its length. We wish to determine the electric field intensity at the center of that arrangement, right over there. So we consider, just like we did in the previous case with the circular coil, what we do is we take two elements dl, and they are taken from this central line that would have divided it into equal halves. What we do is we consider them at angles theta from that central line, and these dl elements with their small length, they subtend a very small angle d theta each, that has been provided over here. So d theta each, and they will be having an electric field directed away from them. So this is considering the charge that has been provided is positive. So dE is along this direction due to this element, and due to this element we have dE prime over in this direction. And obviously, because they are making an angle theta, so these two angles will be theta as well. And so we'll have two cosine components to be acting along the same direction, giving the net field, while the sine components, they are going to get cancelled out, being on either side. So all the elements that we are going to consider in those two halves taken symmetrically, we will have the sine components being cancelled out and the cosine components being added together. So the net electric field is obviously going to be 2 dE cosine theta, and we will be integrating that. Now, as far as the charge distribution is concerned, we have the charge Q to be distributed over the length L. So a unit length will have Q over L charge, and so dl will have Q over L times of dl, so that will be equal to dq. So we have the electric field to be that is dE is equal to k dq over r squared. Now r is the radius that we have considered over here. We'll be obtaining that value of r very soon. So let's say that the radius is r. So this is the value of dE that we have put, and we have the 2 and we have the cosine theta. The dE value, we put the value of dq from this point over here, and we obtain this expression. And now if we look at this thing, that is dl is due to the angle subtended d theta over that radius r, so it is going to be r times of d theta. And so we put that value for dl over here, and we get r d theta. So one of the r gets cancelled out, and we are left with a single r in the denominator, that is over here. So now we have converted this integration that would have been over dl, now that has been changed to over to theta, d theta. And as you know, cosine theta d theta when integrated will give us sine theta, and the angle that we are extending, when this is at aligned, this element is aligned with this direction, then it is at 0 degrees, and as it moves along this direction, it extends right up to pi over 2, that is the 90-degree mark. Similarly along this side as well, so both those sides are going to extend up to 90 degrees, and we have the lower limit as 0, sine 0 is 0, and sine pi by 2 is going to be equal to 1, so that integration will lead to the value 1. So that's been sorted. We are only left with this. Now for the value of r, we know that this pi r semicircle is of length L. So r obviously is going to be L over pi, and we are going to substitute this value of r in this expression, and we get this expression. And now to make it a better looking expression, we open the value of k, that is 1 over 4 pi epsilon naught. So this is 4, let me write that clearly. So this is 4 pi epsilon naught. 2 pi cancels out with 4 pi to give us 2, so that is q over 2 epsilon naught L squared. If you have had it given that q over L is lambda, that is the linear charge density, you would have had a lambda over 2 epsilon naught L. That would have been the value. But because it hasn't really given us any kind of linear charge distribution, linear charge density hasn't been provided in that question, so we are avoiding that. We are just sticking to the values that have been provided to us, the parameters. So that's the 40th one for you. So we keep it up to here, and we'll be trying out more problems in that page that is available to us, that was provided to us. The last 11 bits, out of those, the important ones will be done, and that will be done in the next video in this series, which I hope to make quickly in the next few days. Till then, thank you for watching.